In a universe governed by the very small, lies a science with the power to change everything. Nanoscience explores matter at the scale of 1 to 100 nanometers, where classical physics begins to blur and quantum mechanics takes control. To put that into perspective, a single nanometer is just 1/1000th of a meter. If a marble were a nanometer, then 1 meter would be the size of our entire planet Earth. It's a realm so tiny that a human hair seems like a skyscraper in comparison. But why is this miniature world so important? Because at the nanoscale, size changes everything. As particles shrink, their surface area explodes relative to their volume. This simple geometric shift unlocks a cascade of new properties: enhanced chemical reactivity, strange quantum confinement effects, and entirely new optical behaviors that defy our everyday intuition. Let's look at gold, for example. In our world, it's a familiar, stable yellow metal. But shrink it down to the nanoscale, and it transforms. Gold nanoparticles can appear red, purple, or blue depending on their size. Their melting point plummets, and their chemical reactivity intensifies dramatically. This isn't a trick. It's a fundamental shift in reality. Bulk materials have fixed, predictable properties. But at the nanoscale, color becomes size-dependent. Conductivity can be tuned, and materials that were once inert can become powerful catalysts. These fascinating changes are driven by core quantum principles. Quantum confinement traps electrons within the nanoparticle, altering their energy levels and changing how they interact with light. Electron tunneling allows particles to pass through energy barriers that should be impenetrable. Size-dependent optics give us a palette of colors from a single substance. These are not anomalies, they are the very foundation of nanoscience. To organize this new universe of materials, scientists classify them by their dimensions. Zero-dimensional quantum dots are like artificial atoms, confined in all three directions. One-dimensional nanotubes and nanowires are ultra-strong filaments. Two-dimensional materials, like the revolutionary graphene, are single atom-thick sheets with incredible properties. And three-dimensional nanocomposites combine these building blocks to create advanced materials with tailored functions. So how are these nanomaterials made? There are two primary paths. The top-down approach is like sculpture. We start with a bulk material and carve it down using techniques like lithography, etching, or ball milling. The bottom-up approach is more like masonry. We build structures atom by atom. This involves elegant processes like chemical self-assembly, where molecules spontaneously arrange themselves into ordered structures, or chemical vapor deposition, which grows materials one atomic layer at a time. Of course, to engineer the nanoscale, we must first see it. Since nanomaterials are smaller than the wavelength of visible light, traditional microscopes are useless. We need more powerful tools. Scanning electron microscopy gives us high-resolution surface images, while transmission electron microscopy lets us peer right through a sample. Atomic force and scamming tunneling microscopes allow us to literally feel and move individual atoms. And techniques like X-ray diffraction reveal the precise atomic arrangement within a crystal. The journey to this invisible world began as a bold idea. In 1959, the brilliant physicist Richard Feynman delivered a lecture titled, "There's Plenty of Room at the Bottom," imagining a future where we could manipulate individual atoms. His vision started to become reality in 1981 with the invention of the scanning tunneling microscope. Just a few years later, in 1985, scientists discovered buckyballs, a new form of carbon. And in 2004, the isolation of graphene launched a global revolution in materials science. Today, nanoscience is no longer a futuristic dream. It's actively revolutionizing our world. In medicine, nanoparticles are being designed for targeted drug delivery, attacking cancer cells while leaving healthy tissue unharmed. In energy, nanoscience is boosting the efficiency of solar cells and creating next-generation batteries. Our electronics are getting faster and more powerful thanks to quantum displays and the development of qubits for quantum computing. And in environmental science, nanomaterials are providing new ways to purify water and clean up pollution. But with this great power comes great responsibility. As we move forward, we must consider the ethical implications of this technology. By embracing safe-by-design principles, encouraging responsible innovation, and fostering public awareness, we can ensure that the future of nanoscience benefits all of humanity. From the vastness of space to the intricate dance of atoms, Nanoscience proves that the smallest things can and will create the biggest impact. The future is being built atom by atom.